All right, so yesterday we began this section of 3.1, logarithms and that kind of stuff, but it was very quick. I only got through the first page of the notes, so that was more of an introduction to logarithms. The most important thing that you needed to have taken away from yesterday was that exponentials and logarithms are inverse operations. So if you want to cancel a logarithm, you need to use a matching exponential base. You want to cancel an exponential base, you need to use a matching logarithm base. As long as the bases match, exponentials and logarithms cancel each other out. That's what we talked about yesterday. Let's conclude this section of notes. So we were told to evaluate each of these expressions, and we do not need a calculator to pull this off. You see, log base.
Wait, so
Holy cow, that was loud. Yes, what?
would the answer to C be
Wait,
five
what,
or
we're
one?
not there yet. We jump into 5. We're not there yet. I'm on A right now.
Oh, my bad.
Okay, all right. So, part A. Log base 2 has a job. Log base 2's job is to cancel exponential base 2. It can only do its job if the argument 16 is a power of 2, and guess what? It is. 16 is 2 to the 4th. So what we would do is we would write this as log base 2 of, wait, am I recording yet? Let me make sure I'm recording. That way I'm not wasting my time. Yes, it's recording. Okay, good. Log base 2 of, instead of saying 16, we'll say 2. Okay, I should have known I was recording because the computer will not move quickly. 2 to the 4th. Log base 2 gets to cancel exponential base 2, leaving us with the value of 4. So log base 2 of 16 is 4. Log base 5 has a job. Its job, cancel exponential base 5. And it can only do its job if its argument is a power of 5. And yeah, square root 5 can be written as a power of 5. That would be 5 to the 1/2. Log base 5 does its job, cancels exponential base 5. Oh no, that's not the right color. It's still not the right color. What is wrong with this board? There we go. Giving me a value of 1/2. So part C, I've already had 2 people ask me about part C. You see, the first 2 that we did here, you saw a logarithm canceling an exponential base. But true inverse operations will cancel each other in either order. So if log base 2 cancels exponential base 2, then exponential base 2 cancels log base 2. What I have here going on in part C is an exponential base 4 raised to a log base 4. Since those are inverse operations, exponential base 4 and log base 4 will cancel each other in either order, leaving you with the value of 5. Yep, there's absolutely nothing to even change. You just see that exponential base 4 and log base 4 are inverses and they cancel each other straight away. So the question from one of my Zoomies, I'm not sure which one it was, they were wondering if the answer was 1 or 5. So why did they think it was 1? I'll tell you why. Because they were trying to say that this 4 raised to the log base 4 became a 1 and still had an exponent of 5. And then that's not how it works. When you cancel an exponential base, literally the base is kicked out from underneath the exponent falls down to become a whole number. So it doesn't remain an exponent. So this would not become 1 to the 5th. It's like, well, I would do it, but it doesn't really have the same effect on a video because you can't see what I'm doing on the YouTube video. But when I teach this to the Algebra 2 kids, what I do is I take one of my stools that I have and I put something on it, like my water bottle or something. And then I go, the stool represents exponential base, the water bottle's an exponent, let me show you what a logarithm does. And I kick the stool out from underneath, the water bottle hits the ground. And I go, see, the exponent fell. And then it kind of drives that idea home. But yeah, that's what is going to happen here. The 5 falls down and just becomes the number 5, not 1 to the 5th. Cool? Good now? Great. The common log. What is the common log? Well, I don't know if you knew this or not, but our number system that we use to count with is a base 10 number system. Every single number that we have is technically an exponential base 10 number. That is why our places in our numbers are called the ones place, the tens place, the hundreds place, the thousands place. Those are all powers of 10. And then you have the tenths, hundredths, thousandths. These are also powers of 10. They're negative powers of 10. So our number system is base 10. Because our number system is base 10, most of the logarithms that we deal with are log base 10. They're so insanely common that mathematicians just got lazy and thought, we don't want to write that base 10 all the time. We have to use it so often. How about we all just agree that most logarithms are base 10? So if we don't write a base, we all just agree that it's a 10. And that's what's happening. If you look at your calculator, it has a button that just says log. That means log base 10. We call it the common log. It's kind of like how when we write a square root, we don't put the index of a 2 on it, but we all know it's a square root, a second root. Log, just saying log, means log base 10. It's the same idea. So logs of base 10 are called the common logarithms because our number system is base 10. Here we go, mathematicians get lazy, base 10, yada, yada, yada. I've already said all that. Therefore, if you y equals log base x is true only if 10 to the y equals x. It's just the same idea that I said about exponentials canceling logarithms and logarithms canceling exponentials as long as the bases match. And the rules that we went over yesterday still hold true. Log base 10 is not a special log. It's just a lazy log, I guess you could say. We don't want to write the 10. So all the rules are still the same.
Why is it that the people who literally wrote out hundreds of digits of pi, which is an incredibly difficult math thing to do, are too lazy to write the number 10?
Well, that's because it's curious to know what the next number of pi would be. It's boring to write the number 10. We just don't want to do it all the time. You calculate the next number of pi using something called successive approximations. Yeah, it's ugly.
How many numbers of pi are we up to?
I don't know. Millions. So we're going to evaluate these things. Just more logarithms. No calculator necessary here. So you say, what is log of 100? Well, remember, without the base, the assumption is that it's base 10. So log base 10, common log, can only do its job if its argument is a power of 10. Well, 100 is a power of 10. 100 is 10 squared. So log base 10 cancels exponential base 10, leaving us with the value of 2. I think you can see where this is going. The next one, fifth root of 10. Yeah, that is a power of 10. That's 10 to the 1/5 power. Oh, if you would like to write the base 10, go for it. There's absolutely nothing wrong with that. It's like writing the index of a 2 for a square root, or writing a 1 in front of an x. There's nothing wrong with it. It's just not something you have to do. For part C, there's not even anything to do. Exponential base 10 and log base 10 cancel each other in either order, so boop, answer 6. Something interesting just happened. I told you a minute ago that our entire number system is base 10. What that means is any number can be written as a power of 10. Any number. Part C, what you see is the number 6 written as a power of 10. So if they say, hey, I want you to write the number 7 as a power of 10, I go, is 7 a base 10 number? You go, of course it is. 7 is 10 raised to the log of 7. There you go. I mean, it's kind of a cheesy way to do it, but it's possible. Yeah, so every number can be written as base 10. Guess what? Every number can be written as any base I want. Is 7 a base 2 number? Sure it is. Sure. Here, let me prove it to you. There you go. I just wrote 7 as a base 2 number. So it's a neat little trick that you can do with any number that you'd like. But it's more obvious when you're dealing with base 10s.
You know, for those days when you want to be freakishly complicated.
Well, no, it's not that you're trying to be complicated. It actually does become useful sometimes to help you evaluate logarithms or even solve log equations. It is a very useful concept. I promise you. Now let's see, the last one. Is 1 over 1,000 a power of 10? Yeah. You see, 1,000 is 10 to the third. So 1 over 1,000 would be 10 to the negative third. So we have a value of, nope, I don't want to use red. I'm going to use green today. Have a value of negative 3. There you go. So the next 3 examples, it says use a calculator. So you literally just pick up your calculator and you figure out what log of 34.5 is. Now, depending on which calculator you're using, if you're using the battery-operated TI-30XA that you had to use on the FSA, you have to type the argument first. So for that calculator, you would have to type 34.5 and then you hit the log button. If you are using a graphing calculator or the TI-30X2S, the solar-powered one, the better calculator, you just type log and then you type 34.5. Be a good mathematician. Close the parentheses. The 30X2S will open a set of parentheses for you. You go ahead and close it. Either way, you're going to get the number 1.538. So I want to be really clear here. I don't expect you to know that log of 34.5 equals 1.538, but what I do expect you to know is that log of 34.5 is between 1 and 2. I expect you to know that. Here's why. It shows a deep understanding of logarithms. Well, then how would you know it's between the numbers 1 and 2, Max?
Because it's anywhere between, the log is anywhere between 10 and 100.
Right. So because the number 34.5 is between 10, which is 10 to the first, and 100, which is 10 to the second, we know this log value is between 1 and 2. So it's a really good skill to have. So for the next one, log of 0.43. Without looking at my paper, you see I'm not looking at my paper, and you guys are the first people that I've said this to today. Log of 0.43. Well, here's what I know. 0.43 is less than 1. 10 to the 0 would have been 1. I know this thing has a negative value. In fact, because it's bigger than 1/10, I know I'm dealing with a number between 0 and -1. Oh, look, negative 0.367. Now, I didn't know what that was going to be, but I did know it was going to be between 0 and -1. You see, if you can think your way through these things like that, you have a deep understanding of what a logarithm is doing, instead of just, oh, I can get answers. Do you understand what they're doing?
Are we going to have a calculator and non-calculator parts of this test?
That's a very good question. I don't remember if there's a calculator portion and a non-calculator portion of the test. I have to look. But it feels like there should be. I will check. I don't remember. But it feels like there would be a two-part test.
When you do log C, it says error when you type in -3.
Wait, log of -3 says error? I wonder why that happened.
You can't take a negative number, a log of a negative number, because that's imaginary.
Yeah, you see, the log of a negative number is imaginary. It's complex, but why? Remember, log says log base 10. So you just ask your calculator, positive number 10 raised to what power gives me a negative value? You can't raise a positive number to any value and ever get a negative solution. Remember, all exponential functions have a horizontal asymptote at y equals 0. That is why the domain of the logarithm, meaning what things am I allowed to put into the argument, is numbers larger than 0. Positive numbers only. So this is undefined.
Wouldn't the answer be 3 higher though?
No. If you would like to know how to find the logarithms of negative numbers, I encourage you to check out the YouTube channel Black Pen Red Pen. He does those kinds of things. There's one on his channel. It's really neat. It involves some mathematics that you've never heard of or seen before, but it's still neat. I wish it was as simple as like 3i or something like that, but it's not. So it's undefined. It violates the domain of a logarithm. You can't raise 10 to any power and ever get a negative result. Just like you can't raise 10 to any power and ever get the result of 0. You will only ever get positive results. Argument must be positive. We cool on that page there? Can I move on? No screams of terror, so we will move on. So I've asked you to solve these equations by changing it to an exponential form. I can't stand the, well, I just know the answer, which is kind of what you're taught to do in Algebra 2. Well, you just see the answer through some kind of weird reverse magic. No, there must have been algebra behind your answer. What is the algebra? Okay, I'll tell you what the algebra is. we're going to cancel the logarithm. It is log base 10. In order to cancel log base 10, I need a matching exponential base. That's exponential base 10. So what you do is you, and this is quote unquote, okay, you base 10 both sides. And you know what? Sometimes that confuses students, so let me write it even better. What you do is you pretend that both sides of this equation are exponents and their bases were something whatever you wanted them to be. So we chose 10 because it would allow us to do this. Whee! So what that tells us is that that argument, that unknown number in there, must have been 10 to the third, which is 1,000. It's so much better than just saying, well, I can just see the answer's 1,000. Because then someone that doesn't understand logs goes, why? And you go, well, because 10 to the third is 1,000. And they still don't understand why. That's why.
And you tell them, neither do I, but that's what I know.
Yeah, now there's no reason to wonder. And so there was a question in the room as well.
I said, what would be the
That is the exponential form. X equals 10 to the third. That is the exponential form of that log statement. But it's 1,000 is the answer, is the result. So for part B, I know that the answer is 32. But is it good enough for me to just say the answer is 32? Don't you see why? No, it's not good enough. But that's what we kind of ask you to do in Algebra 2, unfortunately, because I wasn't your Algebra 2 honors teacher. So here's what you should do. You need to isolate x. The only way to isolate x is to cancel log base 2. So you use a matching exponential base. You say that both sides of the equation are base 2. The left side has an exponent of log base 2 of x, and the right side is the exponent of 5. You conveniently chose a matching exponential base so that you could do this. Whee! And you go, oh, there it is. That unknown argument, x, is 2 to the 5th. So there's the exponential form of that log statement, but the result is 2 to the 5th is 32.
I don't remember like how to actually do it the other way,
Mhm.
but I still got the answer because it's just I don't know. I guess I'm
You
trying to do
saw the answer, but you didn't use algebra to get to your answer, you just saw it.
You just knew you have to swing the thing out.
Yeah, you just knew you had to swing the thing out, but you never understood why you were doing that in Algebra 2. You were just told this works. I encourage you to think of it this way, because if you think of them this way, solving log equations will be very easy. Because that's where we're heading, solving log equations. Not today, but we are heading there eventually.
Those not to do, I don't
Yes, you did. And you probably repressed them from your memory because they were painful. They won't be painful any longer. The natural log. Have you ever wondered why there was 2 different kinds of logs? Why there was log and ln? Did you ever wonder that? To make it difficult? No. You don't want to know why there's 2 different kinds of logs? Because of laziness. That's why.
There's 2 different kinds of logs.
There's not, though. That's the thing. It's lazy. There's not 2 kinds of logs. Mathematicians don't like to write crap over and over and over again. So when something becomes insanely common, mathematicians back in the day would usually just come up with a unique symbol for it. E, the number E, is known as the natural base. It's the natural base. And it is actually insanely common in mathematics. It shows up all the time. So since the natural base E showed up all the time, that necessitated, that's the word I'm looking for, that necessitated its inverse to show up all the time as well, log base E. Mathematicians got sick of writing log base E. Log base E is ln. ln stands literally for log of natural base. That's what the L and the N are. So ln is log base E. Let's be really clear here. ln does not have a base. It's just ln because ln is a lazy way of saying log base E. I had an Algebra 2 student a couple years ago, 2-3 years ago, that will go to his deathbed saying that ln is base E. I'm like, no, ln is ln. ln represents log base e. It just killed me, and there's a difference. ln is just a quick way of writing log base e. It stands for log of natural base. So if you ever need to cancel natural base e, you would use log base e, which is ln. And if you ever need to cancel ln, which is log base e, you'd use exponential base e. It follows the exact same rules. It's just a quick way to write log base e. That's all it is. So all of these things that are written here say exactly the same crap that was in the other box. It just has e's and ln's instead of tens and log base tens. But it means the same thing. So there's no reason to even talk about it. It's like you just move on. As long as you can accept that ln is log of the natural, you're straight.
No writing log e.
If you would rather write log base e, you absolutely can. But you need to understand that it is ln because that's the button that's on the calculator.
Yep.
But as long as you understand that, shoot, that fine, go for it. Absolutely. So ln has a job. Log base e has a job. Cancel exponential base e. That means in order for it to do its job, that argument must be a power of e, and it is. It is e to the 1/2. You may have noticed that I write my ln's with a cursive L, but not my logs. Why? I do that so that it doesn't look like in. That's really the reason why. And also because that's the way my math teacher did it. So I just ended up writing it the same way he did.
You went into this football class,
Mhm.
you went the entire chapter thinking
Yeah, of course they did. Did she use the cursive L?
I don't know.
She probably doesn't.
She did.
So she used a cursive L?
She used the cursive L for both her logs and
Oh, she used it for both?
yeah,
Do you know why she probably used the cursive L for log?
because her husband is also
Because her husband did it, which is where I learned it from. Or, more than likely, they both learned it from their math teachers. Because it's just easier. I actually tutored a math teacher a couple years ago because they were a long-term sub. So just kind of took the job of math teacher but was not certified to teach math. And I said something yada 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 about ln, and dude goes, "Oh, is that what the in on the calculator is?" And I was like, "Oh my god, you have to teach that next chapter, right?" Didn't know anything about it, and I had to teach a teacher all of the logarithm chapter before he had to teach it to his students. Luckily, I'm good at teaching logarithms. Okay, so
That's his fault.
yeah, it really is. It comes in handy often. So check this one out. Boink, 5. I mean, don't overthink it, please. ln cancels base e, and check this one out. Boink, e cancels ln. I mean, they are that easy. But it's because log base e cancels exponential base e, and exponential base e cancels log base e. That's why that's working. Now, a minute ago, we evaluated logs, common logs, on our calculator. This just says evaluate the natural log on the calculator. It's done exactly the same way. If you want to use the battery-operated TI-30XA, you type 23.5, and then you hit the ln button. Bless you. If you would like to use the solar-powered, much better actual calculator, TI-30X2S, you type ln, it opened a set of parentheses. You type 23.5, and you be a good mathematician, you close those parentheses. Don't leave hanging parentheses. Either way, ln at 23.5 is 3.157.
I feel like you keep dissing us people using the TI-30XA people.
What happened?
You keep saying the better calculator when we were stuck with the
Oh, yeah. That was you're stuck with the other one because it doesn't show. I think it's because it has a single display, a single line display. That's why they made you use that one, because the 30X2S shows the input and the output at the same time, and that was considered too easy to cheat from.
where's the non-log and like anything other
So he wants to know how to use a different kind of log base on his graphing calculator. Can it do it?
We couldn't hear you for part of that.
What's that?
We couldn't hear you for part of what you were saying.
I think I might have gotten too loud or too close to the microphone, so the noise gate kicked in and shut me off. He wanted to know how to use the graphing calculator to do anything that's not base 10. Can it do it? Absolutely. But we'll learn that at a later point in time, okay? So ln of 0.48 is negative 0.734. Notice that I didn't tell you that I expect you to kind of understand that this would have had a positive or negative value. That's because e is an ugly irrational number, and it's difficult to think about powers of 2.712. Uh-oh. Yes, have I messed up? Oh, okay, what's up?
Is it the same as like the part A and then 1?
It kind of works. Yeah, it works the same way. It's just hard to think about powers of things with decimals. But it's exactly the same. So you go, okay, e to the first is 2 and change. Think of it like this. 2 and change is less than 3, right? So 2 to the third, no, I said 3 to the second, there we go, that's what I was getting at. 3 to the second is 9. So e to the second is less than 9. You see how I'm doing this? 3 to the third is 27. So e to the third is less than 27. 3 to the fourth is 81. So e to the fourth is smaller than 81. Oh, this log had to be somewhere between 3 and 4. But it's a much harder thing to pull off because you have to go, it's almost 3, but it's less than 3, so its powers are going to be less than the powers of 3. It's just not worth breaking your brain over. I mean, if you wanted to, you could. I'm more worried about, can you do it with integer bases? But yes, it's the same idea. It's just harder to think about. And remember how I said that the argument of a logarithm must be positive? LNs are logarithms, so this is undefined. You don't even have to think about it. The moment the argument of a logarithm is negative or 0, undefined.
And now for graphing.
Oh, yes. And then we end with graphing. When we did section 3.1, which was exponentials and logistics, and specifically exponentials, we did some very basic exponential graphing. So for these notes, we will end with some very basic logarithmic graphing. So do you need to only have a basic understanding of it? No. No, I'm going to expect you to have a deep understanding of graphing, and that is why tomorrow we will specifically be focusing on how to graph exponentials and logs that are not basic. And even further, we will look at graphs and write their equations. Okay? But very basic.
We had to do that on our homework the other day, but you never went over it.
Oh, well, you'll know how to do it soon. The parent log function, y equals log base b of x. But it could also have been ln of x because the base could have been e, right? This is the same basic shape. You notice that it has a vertical asymptote at the y-axis. The reason why this has a vertical asymptote at the y-axis is because its inverse, the exponential, has a horizontal asymptote at the x-axis. Remember, all the x's become y's and all the y's become x's? That means the asymptotes change places as well. Notice there are 2 points on that picture, 2 very specific points. Those points are 1, 0. The reason why is because if you plug in a 1 to a logarithm, the moment its argument is 1, that log has a value of 0, and that's true for any log. And then I gave you base comma 1, and that was from the other special logarithm that I talked about yesterday, log base b of b always equals 1. So what I'm telling you is, you only need 3 objects to graph a logarithm. You need its vertical asymptote and 2 points, and that's it. That gets you a good sketch of a logarithm. And that's what we're going to be doing tomorrow especially, but today it'll be very, very easy. Domain, well, you can see it. It only exists to the right of 0, so greater than 0, from 0 to infinity. Its range, though, it's up and down forever, all real numbers. It's continuous on its domain, so it's continuous from 0 to infinity. It's an always increasing function, just like the parent exponential is always increasing. It has no symmetry, it is not bounded at all because, range is all real numbers. No extrema, no horizontal asymptotes. Does it look like it's kind of flattening out to the far right? Kinda, but it's not. It's just like how the parent exponential looks like it's turning into a straight up and down graph, but it's not. It just grows insanely slowly. Vertical asymptote, we've already said it, is x equals 0, and it has end behavior as x goes to infinity. I wrote ln of x. Whoops. Well, it's just supposed to say log base b of x rises to infinity. And I missed one somehow or another. The other one is the limit as x goes to 0, log base b of x goes to negative infinity. That means it shoots downwards as you approach its vertical asymptote. That's what that says. I'm not going to ask you in behavior of logarithm questions on tests, though. It's just good to know it. And that leaves us with 4 graphing questions, and they are pretty darn basic. It says, describe how to transform. Yeah, I skipped over that. I'm done talking about transformations. We're just going to sketch the graph. That's what I really care about. We're going to sketch the graph. Huh? Oh, okay. We're going to learn how to sketch the graph. So when you get to the homework, if it says describe the transformation, you can if you want to, but feel free to not if you don't want to. Okay? It's completely up to you. Hey, look, someone's printing to my printer. Yay! Wasting my toner and paper. So what we have here is ln of x plus 2. ln of x plus 2. Well, its domain, remember, is decided by the argument. The argument must be a positive number. So x must be greater than negative 2. Guess what you just found? That's the vertical asymptote. Vertical asymptote is x equals negative 2. So how do we find those 2 pretty points? Let's call them the pretty points. How do we find those 2 pretty points? They're always found the same way. Oh, do I have some space right above this? Yes, I do. 2 pretty points are found like this. Asking yourself, what x makes, and I'm going to say arg for argument, equal 1. You need that number. Because when the argument is 1, the log's value is 0. And that doesn't mean the entire function equals 0 because there could be some transformations, but the log's value is 0 when the argument equals 1. So for us, what?
-1.
Yeah, x equals -1 makes the argument be a 1. So if I plug in a -1, I have ln of 1, which is 0. And the other thing you're going to ask yourself is, what x makes the argument equal the base? Basically, you're trying to force the 2 special logs. And the reason why you want this is because the log's value, well, my computer's lagging hard right now, is 1. Does that mean the function has a value of 1? No, there could be transformations. But the log's value would be 1. So for us, what x would make the argument equal the base? Now that's a tricky question. And the reason why that's a tricky question is because your base is e, right? So what number would give us 1 in there? Well, you'd have to do like x plus 2. You'd have to, well, don't use it as a decimal. We're just going to kind of like logic our way through it. we need x plus 2 to equal e. That's what we need. So this is kind of difficult with ln's, but what it's going to be is e minus 2. What a weird thing to write, e minus 2. But since e has a value of 2.712-ish, that's somewhere around 0.712-ish. Oh, goodness me. I've written a 0 as the y value again. Come on, panel, catch up. Actually, it's not the panel. Come on, computer, you can do it. I hit undo twice. Thank you. There we go. So somewhere around the value 0.712, you have a value of 1. So we're just going to, make the dot fat enough and people can't argue with you. So your sketch looks like this. There you go. Ta-da. Awesome. Pretty ln graph. There it is. Part B, well, that's just a vertical stretch of the parent log function. So that's really simple. What's my base? 10, yeah.
And
Yeah, it's a base 10. So when you say what number makes the argument equal 0, you would just say 0. And the log's value at 0, crud. I said it backwards. What I was trying to say was, what makes the log's argument equal 1? The answer is 1, because it'll have a value of 0 at that point. So you have 3 times 0. Sorry, I misspoke. 1 comma 0. That's here. And then you're supposed to figure out what number makes the argument equal base. What's the base of this log? 10. So the other special point is at 10 comma, oh my goodness, my grade only goes to 4. Don't worry about it. If you plug in a 10, log of 10 is 1, and then times 3. Because I did not shift left or right, the vertical asymptote is still the y-axis because the argument must be a positive number. You just say x has to be greater than 0. That's its domain. So what am I going to do? Well, here's what I'm going to do. I'm going to come up, I'm going to go through this, and then I'm going to do like that. You see how I stayed below 3? We understand that I'm not going to reach the y value of 3 until I get to x equals 10. At least you understand what the shape would have looked like. I'm thrilled. That is good enough for me. Cool? Yeah.
are we going to do a few more examples? Because I don't completely understand the math behind it.
Yeah, we're going to do more. We're doing the last 2. Is that what you asked me?
Yeah, I don't completely understand the math behind it though, so could you explain that in a similar way?
Well, the special logs that we talked about yesterday are log base b of 1 and log base b of b. So we're trying to figure out what we would have to plug in to get log base b of 1 and log base b of b. So for example b, our base is not written, therefore that base must be a 10. So what number would I have to plug in to get log base 10 of 1? I'd have to plug in a 1. And log base 10 of 1, which is what's happening right here, is 0. So you have a 0 times a 3, you have a 0. Remember, that is log base 10. So you ask yourself, what would I have to plug in to get log base 10 of 10? Well, you'd have to plug in a 10. So here, you plug in a 10. You now have 3 times the log of 10. The log of 10 equals 1, though. So it's 3 times 1. We're trying to force the special logs. We're trying to force log base b of 1 and log base b of b. And tomorrow we'll graph a lot more, and it should be even more clear tomorrow. Right, remember the argument must be a positive number. So 3 minus x must be greater than 0. If you add x to both sides, you get that x must be less than 3. What you found then is that your vertical asymptote is at x equals 3. But you are going to be less than that, so we are going to go to the left. That's going to be the result. Now, unfortunately, yeah, it's an ln again. So remember, we're trying to force the argument to be equal to 1. So what x would I have to plug in? 2, because 3 minus 2 is 1. So our first special value is going to be at 2 comma. Now let's see. ln of 3 minus 2, that's ln of 1. Oh, ln of 1 is 0. Because no matter what the argument's base, no matter what the logarithm's base is, the moment the argument equals 1, the entire log equals 0. So we have a point at...
When you find a vertical asymptote, is the asymptote always 1 over 0?
No, it's not always 1 to the left or right of the vertical asymptote, because I could horizontally stretch this thing. And it's not always at 0 because I could shift it up or down as well. We'll do all that tomorrow. These are the basic ones. And the other thing we'd have to do is make the argument equal base. Oh my goodness. So you have to go, okay, 3 minus x equals e. So x, if you added x and subtracted e, it'd be 3 minus e. What an ugly thing to say, 3 minus e, comma, 1. Because when the argument equals base, your log is a value of 1. 3 minus e. That's 3 minus 2.712-ish. So we're somewhere around the 2 point or 0.288-ish, I think. Quick maths.
3 minus, oh, yeah.
Somewhere around the 0.288-ish mark. A 0.288-ish. Not sure what I said. That's like here, whatever. Feel free to use a calculator if you want to know what that number is. And the last one. That, it's written in a weird way, but that's been shifted up 1 unit. Well, your domain is decided by your argument, and the argument must be positive, right? So you go, okay, argument is x. Oh, x must be positive. X has to be greater than 0. What that tells you is that your vertical asymptote is still the y-axis. Cool. The 2 special logs are what we're hunting for. We want the argument to equal 1. Well, you'd have to plug in 1 to get that. So now you have 1 plus log of 1. Log of 1 is 0. That's 1 plus 0. So you have a point at 1, 1. And then lastly, special log is you want the base to match the argument to match the base. We want log base 10 of 10. The only way to get that is to plug in 10. What this has now is 1 plus log base 10 of 10. That's 1 plus 1, or 2. Again, that 10 is way off the grid. So when you sketch this thing, don't get anywhere near the 2 as you come up. It's like that. So it'll be a little while before you get to 2. You need to go all the way out to x equals 10 to get to y equals 2. But that's it. Tomorrow we will graph much more complex logarithms, and I feel like when you graph the more complex ones, it'll make a lot more sense on how to graph them. The extra credit is just evaluating 6 what I call challenging logs. But now that I've taught you how to do it, I doubt they're going to be very challenging.
Is the extra credit in the course material?
The extra credit is in the course materials, and like I said, it'll be due Monday. For now, when you go to do the graphing questions at home, if you're still confused, just use your graphing calculator and try to understand why it is what it is and sketch that. Tomorrow, when we do the more difficult graphing questions, I think it'll be more obvious. Especially because I'm going to do other bases like base 2 and base 3 and things like
Are
that.
any of them going to be like LN or anything?
In the homework or tomorrow?
In the homework?
It might be.
Well,
That's
then-
why I'm saying I don't want you to break your brain about what.
Then we need to know how to put in like base. Are there only
No, you just use the LN key.
Oh, okay. It's gonna be LN.
Yeah, you just use LN.
It says here that the homework's due on Friday.
What?
Looking at the thing, it says homework due Friday.
Yeah, it is. Because we finished the notes today, so the homework is due tomorrow. But the but the extra credit's not. Yeah, the extra credit's not due till Monday.
I'm over here like thinking that it was due today or that it was Wednesday. I don't know what.
Well, you did have a weird week, so that's understandable.
I can't believe it's already Thursday.
I wish it was already Friday. Oh boy. All right. I'm going to stop sharing with you all, and I am going to clear that slide. Eventually, it's going to clear that slide. There we go. Reset the height. This is what I'm doing with these Algebra 2 kids today. Will not be recording these notes.
Yo, quick question. You wanna read?
Wait a second. Uh-oh. Did it record that screen? What am I looking at here? Preview? Oh, I forgot to stop recording. Ha.